Today in physics, we'll be talking about the Atwood machine under the effects of friction. This is part 6. So we have a massless string that is hung over a cylinder. We have two weights, weight A and weight B. Weight A has a mass of ma and weight B has a mass of mb, where mb is less than the mass of A. Now we give B an initial speed of v0 downwards, and it starts off at the initial point O. Then, once we give B an initial velocity, it moves down to the lowest point. Once it reaches the lowest point, it starts moving upward. Then it passes the original point O again. We're given that the coefficient of static friction, namely mu s, is equal to 1.0, and the coefficient of kinetic friction, mu, is less than the coefficient of static friction. So we know that B is going to turn around at the lowest point, and it's going to pass once again through the point O. When it does, we want to figure out what V1 is, where V1 is the speed of weight B at the instant it returns to O. So V0 is the initial downward speed given to B when it starts off at O, and V1, which we are trying to find, is the final speed of B when it returns to O, and V1 is an upward speed. In order to solve for V1, let's split up the motion of the system into two parts. The first part is when B is going downwards, and its acceleration, however, is going upwards. And the second part is while B's motion is moving upwards, and its acceleration, before it reaches point O, is also still moving upwards. So let's start off with the acceleration while B is falling. So let's denote AD as the upward acceleration. So the upward A while B is moving down. So while B is falling. And it's falling because we gave it an initial V0. Now let's draw some force diagrams on A and B. The tension on A, we'll call it T0, acts upward along the string that connects A to the cylinder. And the force of gravity also acts upon A, namely ma times g. Similarly, B has a force of tension acting upon it, we'll call it T1. And it also has a force of gravity acting upon it, namely mb times g. So now let's write the net force equations for objects A and B. So for object A, we have ma times ad is going to equal, and in this case for A, the acceleration, it's also given you can think of it as object A is also given an initial velocity of v0, so it's going to also move upwards. But similarly to how B's acceleration is upward, A's net acceleration in this beginning phase is downward, since although its motion is upward, it gets slowed down more and more until it finally starts turning around and starts accelerating downward again. But for B, the acceleration is upwards. So when we're writing the net acceleration equation for A, we find ma times ad is equal to, that's a downward, and we define downward as positive for object A. So we have ma times g. The force of gravity is also positive since it's acting downward. And what acts against it is the tension force, namely T0, which is acting upwards, so we subtract. We also have the net force for object B. In this case, object B's net acceleration is upward, so we follow the signs to have T1 minus mb times g. Since the tension force is pulling upward, which is its net acceleration on B, while the force of gravity is acting in the opposite direction, so T1 and the force of gravity on B have opposite signs. Now, when we're solving for T0 and T1, we find that T0 is equal to MA times G minus MA times AD, and T1 is equal to MB times AD plus MB times G. We also have a relationship between the two tangents, namely T1 is equal to T0 times e to the mu 0 pi, where we got the coefficient of e to the mu 0 pi due to friction, and the derivation can be found in part 4. Now, we have T1 is equal to T0 times e to the mu 0 pi. Since friction is going to help work against B, it's going to impede the motion of B, since friction works against the motion of the system. And initially, the system is moving downwards. It's moving clockwise, since we give B an initial velocity downwards, and friction is going to work in the opposite direction. So we have this equation. Now we can plug in what we know T0 and T1 to be into our equation, so we get that MB times AD plus MB times G is equal to T0, which is MA times G minus MA times AD times e to the mu 0 pi. Now we want to solve for AD, so let's move all those terms containing AD to one side. So we get plus e to the mu 0 pi MA times AD is equivalent to e to the mu 0 pi MA times G minus MB times G. So if we factor out AD, we find that it has a coefficient of MB plus e to the mu 0 pi MA. And we can also factor out a coefficient on the right hand side to get e to the mu 0 pi times MA minus MB. Now when we're solving for AD, we find that AD is just equal to G times this coefficient, e to the mu 0 pi MA minus MB over, if we rearrange the terms, e to the mu 0 pi MA plus MB. Now our reason for finding AD was that so we can use this equation, namely the change in kinetic energy is equal to m times A times delta x, namely the work done on the system. So the change in kinetic energy is expressed by 1/2 mv final squared minus 1/2 mv initial squared, and this is equivalent to ma times delta x. We can multiply by 2 and divide by m on both sides, so we get that v final squared minus v initial squared is equal to 2 times a times delta x. And here, when b is moving downward, we know what v final and v initial are, and we just solve for AD, the acceleration, and now we can solve for delta x. Once we solve for delta x, we can use this value of delta x again later on to solve for v1, using a similar equation. So we have our two equations, and now let's solve for delta x. When we're talking about v final, we're talking about the point when b reaches the lowest point where it starts to turn around again. So at that point, the final velocity is just equal to 0. And the initial velocity we were given, the initial velocity is simply v0. So now we have 0 squared minus v0 squared is equal to 2 times AD times delta x. So we can see that delta x then must be equal to negative v0 squared over 2AD. And we can also plug in what we know about AD, namely delta x is now equal to negative v0 squared over 2 times g, and we have e to the mu 0 pi ma plus mb over e to the mu 0 pi ma minus mb, where the coefficient of g in the expression for A was on the bottom, was in the denominator for our expression for delta x, so the numerator and denominator switched. And what we find is that delta x is a negative value since the distance traveled is downward, while the acceleration, AD, was an upward acceleration for B. So what we find is when we were saying delta, the change in kinetic energy for object B is equal to m times A times delta x, what we find is that delta x and A are in opposite directions, and we define AD to be positive, so delta x is going to be negative, which it is. Now we have the second part, namely when B reaches the lowest point and starts moving upwards. So we'll say let AU equal the upward acceleration, so the upward A, while B is rising. So while B's motion is upwards. We have the same free body force diagram as before, and if we write out the equations of motion for the two objects, we'll find that they are also the same. So we'll write it as such, and for object B, it is also the same as before. And the only thing that is different is that instead, last time, when we were talking about when B was moving downward, so when B was falling, our relationship between the two tensions was that T1 was equal to T0 times e to the mu 0 pi. But now we have T1 times e to the mu 0 pi is equal to T0, or in other words, T1 is equal to T0 times e to the negative mu 0 pi. So we simply divided by e to the mu 0 pi on both sides, or we multiplied by e to the negative mu 0 pi on both sides. Both of those actions are equivalent. And the reason why the tensions have changed is that now friction, since the whole system is now moving counterclockwise, namely B's motion is moving upward, A's motion is moving downward, what we find is friction helps to work against the downward motion of A to help try and get B to start moving downwards again. So that's how friction is working. So as a result, we have T1 is equal to T0 times e to the negative mu 0 pi. Now, by following the same logic as before, we simply plug in what T1 and T0 are and solve for AU. So we follow the same steps to solve for AU, and also earlier this was MA times AU, not AD, and similarly this was MB times AU, not AD. So we find that AU, we can conclude, has a relationship with G, namely it is equal to G times e to the negative mu 0 pi times MA minus MB over e to the negative mu 0 pi times MA plus MB, and that's if we're rearranging the terms on the left hand side. So we have this relationship between AU and G. And we can see that it's extremely similar to the relationship between AD and G, except that instead of e to the mu 0 pi, we now have e to the negative mu 0 pi. So once again, we have our equation relating the initial and final velocities, as well as delta x and A, and we have our delta x from before, but this time realize that delta x is positive, since the motion of B is upwards, and it travels the distance delta x, that is upwards, and the acceleration is also upwards. So delta x is going to have the same sign as the acceleration upwards, namely a positive sign, since they're going in the same direction. And we know that delta x from before and the delta x when B is moving upwards is going to be the same, since we're asked what V1 is, where V1 is when B arrives exactly at O when it's coming back up. So the amount of distance that it travels down, the amount of distance it travels up from O to the lowest point, from the lowest point to O again, is going to be the same. We also know that V final is going to equal to V1, because that's what we're looking for, and V initial is going to equal 0, since the initial point is when B is at the lowest point, and when it's at the lowest point, it has no velocity. Now let's plug in what we know and solve for v1. So we find that v1 squared minus 0 squared is equal to 2 times au times delta x. So we find v1 squared is equal to 2 times au, which is also g times ma e to the negative mu 0 pi minus mb over ma times e to the negative mu 0 pi plus mb. And we also multiply by delta x, which is v0 squared over 2g times ma e to the mu 0 pi plus mb over ma e to the mu 0 pi minus mb. So if we cancel out some terms, we find that v1 squared is equal to v0 squared. And we're multiplying by 2g and dividing by 2g. They are canceled out, so we have the two coefficients, ma times e to the negative mu 0 pi minus over ma e to the negative mu 0 pi plus mb. And we have a similar pattern, except it's e to the positive mu 0 pi and e to the mu 0 pi minus mb on the bottom. So we find that v1 squared and v0 squared are related. Once we've taken the square roots of both sides, we come to the conclusion that v1 must be equal to v0 times the square root of the two coefficients of au and delta x that we got from before. So we find that this is the relationship between v1 and v0, where v0 is the initial speed we give to object b, and v1 is the final speed at which object b returns to the original point O. And this time, v1 is moving upwards.